All right, when we are back and we're going to look at developing now our Nyquist stability criteria, excuse me. So we're going to test essentially the stability of a closed loop system to the open loop transfer function. So we're going to link essentially these two things. So let's say we have, this is the closed loop poles. This is our open loop transfer function, as we know. This would be the transfer function in our system. So the Nyquist criteria is basically saying Z is the number of closed loop poles in the right half plane. So, and it would be basically those are unstable. P is going to be the number of open loop poles in the right hand plane. So this is really important. So the number of closed loop poles in the right hand plane, the number of open loop holes in the right hand plane. So we need to look at closed loop poles and the open loop poles. And n is the number of counterclockwise encirclements of this point by the Nyquist plot. So for stability, so the clockwise encirclements of basically being on this -1 here. So counterclockwise, so CCW. So counterclockwise encirclements of that point. So for stability, we need Z equal to 0, so N and P must be equal to 0. If the open loop transfer function has no right-hand poles, right? If this has no right-hand poles, then it's 0. The stability requirement requires no encirclements of -1. So if P is 0, then by necessity, and basically N is not, then we have to have that basically equals, it must be equal to no encirclements of -1. So that is our criteria for stability. Now, it's really important. What about poles at the origin? When your transfer function, your open loop transfer function, has poles on the imaginary axis, so basically if you have an integrator, the Nyquist contour has to be indented in order to avoid singularity. So it will detour around that origin in the complex plane, and we're basically going to analyze at the limit, or in the limit, as frequency approaches to 0, and looking at that. And you'll basically see this kind of large arc in this dash. If our pole is stable, then it does not increase P. But if it does affect the plot shape, it has to be handled carefully. So when you have an integrator and that pole at the 0, we just have to be careful. So this is our open loop transfer function. So we know there's one integrator, there's one pole at 0, and we have two complex poles here, both of which fall in the left-hand plane, and there's going to be a 0 here. So P, the number of open loop holes in the right-hand plane, is 0. So if P is 0, and we need Z equal to 0, N must be equal to 0, so we can't have any encirclements of basically -1. So we need to figure out and solve, because we have that value K, so it can push essentially our pole location. So what's going to be that critical frequency? And actually, we solved for it last time because it's the same transfer function. So I'll kind of save you essentially the math. It's just like what we did last time. And we saw roughly, and we can actually see that there. So 2.97, really it's 3. So if K is less than our 3, if K is less than 3, then we are going to be stable. There's going to be no encirclements of -1. But we'll see here that actually, and we can actually see that in action. So remember, we can't have any encirclements counterclockwise of -1. So let's go ahead and let's put this to the test. And let's go ahead and let's start to increase. So let's say, and actually I'm going to go ahead and just say, we don't need to go too far. Let's go to 10. All right, so now what we're going to do, so 1, and we can kind of zoom in here, or at least kind of look at the coordinates. This is our -1, right? So we don't see any encirclements of this, right? And essentially this is what we're talking about dealing with an integrator here, this dashed line and going around the arc. But we can see here we're not making any encirclements. But let's start to increase. Let's go to 2. And you can see where it's going. Basically, the way this it's curving out is like this. So we're going here, here, and then in here, or basically we're going like this. It's going from here, and then this is the counterclockwise loop. And then here, and then here. So you see we're starting to kind of approach, right? We're not there yet, but we're starting to get close to it. What about 2.9? Oops. Let's delete that. Let's go up here. So you can see here, we're right on the edge, right? So let's get our coordinates. You can see we're almost about touching -1. So if we go to, for example, 3.2, and if we zoom in, I'm gonna go from 0 to 1. And I'm gonna go from -2 to 0. Where are we zoom? It's always hard on these plots to kind of see. But if I go to 3.1, this is perfect now. You see here, we have a counterclockwise loop around that. And if we go even further, it's going to be very clear. You see, we have a loop essentially that encircles. So we're going here, and then it can basically go through here, here. So we're encircling that -1 there. It's a little bit of an odd example, but it's kind of the idea here. Let's look at another one. So now in this system, we have 1, 0, and we have a pole that's in the right hand, that's in our right hand plane. So our P is equal to 1. So for stability, we need to have 1 closed loop counterclockwise around -1. So we can do the same thing. We can calculate that critical gain, and this is kind of like it's a nice little kind of, I don't want to say simple analysis, but it's a cool, straightforward analysis where we can figure out what is that critical gain. In this instance, for this problem, it looks like 2, and what we can see here is if we are less than 2, actually let's go here. So we need that 1 encirclement. So if we're less than 2, again, look at this is going counterclockwise, very simple. Look at, we're not touching that -1. So if I go to 1.9, I'm getting close, but I'm not there. And then if I go above 2, so let's say I go to 2.5, see, I encircle it. So now we're stable. And we can even go to, 50. Not 250, 50. And we see we still have that singular closed loop around -1. So, fantastic. So we are stable. So this is essentially how you're going to analyze these systems using a frequency response. It's a cool analysis. It's very robust. It's very feasible to implement. And it's a very robust analysis. So thank you very much. It's been a pleasure to have you all in the class. And be looking forward to more controls related topics in videos. Thanks. Bye.